So yes, I have been working at the intersection of language and vision, and how to use, especially how to use insights from language and perception into the computer vision problem. And the computer vision problem is really about understanding images. And I guess I don't have to convince anybody why it's important to understand images, because a lot of the information that is produced these days are images. So we want to understand them. And what does it mean to understand images? There are many ways, in which people in computer vision particularly have tried to understand images. If I show you a picture like these, ideally maybe what you want is a set of words. So there is some connection to language. You have an input image and then you produce a set of words in some language, in this case English. And these are some of the keywords that are used in some of the computer vision systems. And you would have things like TV stand, there is a TV stand right there, or fish tank, there is a fish tank in the background. There's also a pit bull here, and there's a feline or a cat. And these are all things that we thought often as image tagging or image classification. If you want some more level of detail, there is a problem that is perhaps slightly more complicated, where you would get also the locations of all these objects. You don't want to just predict what is there, but you also want to predict where are all these things. And even more detail and slightly harder problem, perhaps much harder, and this is called object detection. The harder problem is how to produce detailed masks for each of the objects here. And of course, not all these concepts can be localized. There are things like indoor that refer to the whole scene. And this is the way we're trying to understand images in computer vision. And there are a couple of problems with this approach. And one of them is that if you want to communicate the results of your computer vision system to people, maybe this is not the most effective way, because this is not really the way we understand images. But there is another problem, is that if you want to train a system that can do this, then you need usually supervised methods that require a lot of intensive labeling by people. So you would have to have a lot of people describing images in this way, which is unnatural and makes the task very intensive. Just imagine yourself trying to label all these things one by one. So how do we actually describe, this is called image parsing. How do we actually describe images? And the answer is using language. If you were to describe this picture right here, maybe this is some plausible explanation that you would give for this image. A cat and two big dogs staring at the camera. And you might think that there is less information here than in the outputs that I showed you before. But there is also complementary or extra information. If you notice, the descriptions usually don't mention all the objects in the image. There are things in the background that maybe are not even worth mentioning. So here, the cat and the dogs are mentioned, but a lot of the other background stuff is not mentioned. So there is a notion of object importance in language. And the two dogs are qualified as big, while they might have other attributes as well. The same thing with the cat. The cat is also gray, is also small, or maybe medium size. But there are a lot of things that don't get mentioned in the attribute space. So there is a notion of attribute importance in language. And also action importance. Here the sentence says staring. But there are other actions happening here. So presumably these animals are also breathing, for instance. So there is also this notion of what are the actions that are worth mentioning in text. Things that might be too obvious might be not worth mentioning. So these are things that we decide when we talk about things, and we do it very quickly, and we don't even think about it. Another thing is that in language we have things that might be non-visual or might be visual, but they go beyond what is captured by the pixels in the image at hand. For instance, here the camera gets mentioned because it seems like these animals are looking at something. So it's perhaps the camera, it's perhaps the person who's taking the picture, maybe. So this is information that if you try to predict from the pixels in the image, it will be very hard. How do you predict that camera will be mentioned given this picture? So there is a notion of world knowledge when you produce language. So one of my objectives has been to try to describe images with descriptions. And there are some problems with that approach also. And it's that if you ask several people to describe this image, they might describe it differently. So evaluating the outputs of a system that produces this kind of language is a little difficult. And describing a picture, you can describe it in a very detailed fashion, or you can be very vague also. So there are some problems about how well defined is this problem and what are the applications. But I think it's a very challenging problem, and I think it's a problem that has attracted some attention very recently. But there are still some challenges about how to evaluate the outputs of such system. So I have been looking also at other ways in which we could connect language and vision, and we could study language and vision, perhaps at a more finer level of detail. And one of them is how to refer to objects. These are different kind of descriptions, and these are called referring expressions in the NLP community. If you have a picture like this, and I ask you to describe just one object, but there is a task here. There is a purpose when I ask you to describe it. The purpose is you have to describe it so that I can find the object if I just read these descriptions. And of course, if you have another dog, then you cannot just say there is a dog. So these are some examples of referring expressions for these objects. The dog in the middle, the gray dog in the middle, or the gray dog. So here now, if I hide the bounding box, you can find back what is the object in the picture. And so there is a way to do some verification of how correct are these sentences without necessarily asking people, do you think these sentences are good for this object or this image, which is more subjective. So now you have a way to verify these expressions that is objective. And also, there is less variability between the things that people say here, because now they're talking about, and now there is a task. So you can see some patterns already, even with 3 referring expressions. It seems like the color or the location seem to be important. And another related problem that I'm going to talk about is that we seem to have some preference for certain categories that we use to name objects, real-world objects. And the example here is very clear. Everybody mentioned this object as a dog. But they could have said animal in some instances. And they could have said the animal in the middle, and that would have been sufficient as well. It just so happens that people prefer to use certain words, like dog. And this is another problem that we approach, which is how do we name objects. And this is the problem for which we actually received the Mar Prize, Ali talked about. This is clearly a cat, but it also has all other names that perhaps we don't readily use when we see the object. And this is a problem of how to name things. So during my talk, I'm going to talk about 3 lines of work. How to describe images using natural language, some of the earlier work we did, and some of the more recent work we have been doing on referring expressions for natural scenes and learning how to name objects. So a common theme across these projects is how do we learn from text and how do we produce text to explain visual things. So the first image description system that we came up with was a very simple one. We have an image here, and we assume that we have this huge database with images and descriptions. We just assume that it exists for now. And then if it's sufficiently large, we could think that we could retrieve the most similar images from our database. And these images will have captions. So presumably, we could transfer some of these captions if they are similar enough to our query image. And so this is the way we could have a new image being described by our system. And there are 2 key components of a system like this. One is having a good similarity metric. And we use some standard feature descriptors there that people using computer vision. At least at the time, there are better representations these days. But the most critical part is perhaps having this huge database of images with captions. And how do we do that? I mean, one way is probably we could pay people to give us descriptions and use tools like Amazon Mechanical Turk or other forms of crowdsourcing. But the problem is that that could turn out to be very expensive because we need images with descriptions in a very large amount, perhaps millions. So we thought, why don't we use just the images that are already out there on the web and that already have descriptions? People upload images on the internet and they write sometimes very detailed descriptions. And we use images from Flickr. Flickr has a lot of images. At the time we worked on these in 2011, they claimed they had 6 billion photographs. It must be much larger now. The problem we found is that a lot of the descriptions that we saw there were of this form. They seem to be having a lot of fun. Can you guess what the picture looks like just by reading the sentence? Well, yes, it could be many things. And this is a problem. I mean, a lot of the sentences that we found or the descriptions that we found were not very useful for our purposes. Some of them were too vague, or some of them were talking about things that went well beyond the image. And that could not probably be applied to other images easily. So we want sentences that talk about real objects and how the objects are interacting in the picture. So let's try another example. If I show you this caption right here, dog with a ball in its mouth running around like crazy on the green grass. Now, can you imagine now what the picture looks like? Well, somehow just by reading the text, now we have some idea that the picture will look like something more specific, right? And this is what the picture looked like for this description. So we came up with some ad hoc rules about what are the things that make a caption visually descriptive without looking at the image. So usually captions, some type of captions that are visually descriptive are ones that mention two objects that are physical objects. They are not abstract things, abstract concepts. And they are related to each other by some spatial relationship. So if we look at images of these, at descriptions of this form, they're usually visual, and they're useful for our purposes. So what we did was we collected hundreds of millions of descriptions from Flickr, and then we filter out the things that were most likely not useful. And we ended up with 1 million descriptions, and then we crawl images. And this is a data set that we had in 2011. This is called the SBU Caption Photo Dataset. And it has sentences like, descriptions like these, or dog Zoe in her bed, or Emma in her hat looking super cute. And so they're very visual. They still have some information that might be overly specific, like nouns of particular objects, the names of particular objects. So in that sense, these might not be transferable, but we did something to generalize these captions also. So now we have this database, and now we can complete our loop. We can complete our system. And we can transfer descriptions to new images. And I'm going to show you some examples of the things we retrieved for some images. Here we have this image right here, and it says a strange cloud formation literally flowing through the sky like a river in relation to the other clouds out there. Or this one here says, fresh fruit and vegetables at the market in Port Louis, Mauritius. So these are descriptions that were written originally for other images, not for this image, for some other image in our data set. And it's very interesting that we can retrieve things like these that are very fluent, very correct grammatically, and they're even somewhat creative. But of course, I mean, this doesn't work all the time. I mean, a lot of the times we get things like these, either because here it says Kentucky cows in a field, either because the metric, the visual similarity metric is not good, or we just don't have images of birds like these in our data set. I mean, a million images cannot represent the entire visual world. I mean, I think we can all agree on that. And here is another bad example. So how do we make our system more general? Because if you look at this system, it's just nearest neighbors. And when you do nearest neighbors for things like regression, you usually have a score that you average, and then you transfer the average score to the query image if you're doing something like regression. Now, we have descriptions, so there is no clear idea how do you take an average description and transfer it to the query image. Yes?
So like the description that you have here, the water is clear enough to see fish swimming in the ground. And the one that you have for food for about some other location, like mentioned the city or something, or the market. So these are, is there a test to see are these correct descriptions or are these plausible descriptions? Like, do we actually see?
Yes, I would rather say these are plausible descriptions. They're not necessarily correct in the sense of accurate, detailed information. But they are plausible things that might still give you some idea of what's in the picture, even though if it's not completely accurate at a very fine level of detail. And I'm simplifying a little bit the system also. I mean, we use more than gist and color features. We also use object detectors, people detectors. We use scene classification also to drive the similarity metric. This is the simpler version of the system. But again, I mean, how do we construct new sentences? That was the next question we approached.
So how do you evaluate if the description is correct or not?
We have descriptions for some of the images. Well, actually, we tested these on some images, on some subset, held out subset of our data set. So they have descriptions. So we can compare how many words the descriptions that we generate are in common with the words in the descriptions that people already wrote for those images. Now, this is a very rough evaluation, of course, and there are problems with that, as I said before, because you could have two sentences that have words in common, but they mean completely different things, or you could have two sentences that have completely different set of words, but they mean exactly the same thing. So that is a problem in itself in natural language processing. How do you paraphrase things, or how do you know if two things are just different versions of the same idea, right? So that is indeed one of the problems, but it still gives us an idea of how well we're doing, and we did various tests about how the size of our data set influences the quality of our description set. And as it's very common with these data-driven methods, the bigger your data set, the better the descriptions you can generate, because now you are more likely to find things that are similar in the larger data set. Now, going back to generating descriptions, like really generating descriptions, because now we're just doing transferring. So the next idea was just to retrieve pieces of text, not the entire description, just pieces of text. And just for parts of the image, in this case, for an individual object. Imagine we have this query object here, and we retrieve the most similar dogs in our data set. And we have here descriptions in our data set. So instead of transferring the whole description, we can choose to transfer just some part. And in this case, we're transferring verb phrases, things like laying in the middle of the road, or sleeping under my desk, or sleeping on city street, or laying on the edge of the road. And of course, we have a huge pool of object detections for dogs in our data set. And the way we collect these object detections is actually, in our data set, we have descriptions. So we can run object detectors based on whatever is written in the description. So if it mentions dog, then we clearly need to run a dog detector there. And that's how we retrieve very confident detections in our data set. For the query images, we don't have descriptions, so we have to run a lot of the object detectors there. But here we can get very confident detections and transfer just part of the descriptions. So for one query object, we return actually four types of pieces of text, referring to various parts of the sentence. Noun phrases, verb phrases, these refer to actions. Prepositional phrases, these refer to things that are around the object. And scene phrases, these refer to the whole image. And now we have also scores, which are the similarity between this query object and the object from which we retrieve this piece of text. So these are computer vision scores, if you will. And one idea to generate a new description would be to just pick the best of each type and construct a new sentence, like bird hopping in the sky in a mountain. If you do that, I mean, you could run into very serious mistakes like this one. That sentence doesn't make a lot of sense. A bird would hardly be hopping in the sky. And if you say it's in the sky, maybe you wouldn't mention it's in a mountain at the same time. So maybe there is some other better combinations, like a bird walking near a beach on Long Island. That sounds much better. So the idea was to use language to constrain the kind of things that we are going to mention together. And we use language priors, or how often in text you find the sequence a bird walking or walking near a beach as opposed to walking in the sky. Probably walking near a beach is a very common sequence in text, but not walking in the sky. That would be less common and less natural. So we use these language priors as pairwise scores to select the best combination of text phrases that we're going to put together and assemble into a single description. And this is the basic idea, again, of the system. And you can do this type of decoding using dynamic programming. We actually, because you have unary potentials and pairwise potentials. But we actually did some other things that were more complicated. We solved this as a more general optimization problem so that we can also impose some linguistic constraints on the solution. Like we could have thing here near a beach, and here we could have also on a beach. So you don't want to say things like near a beach, on a beach. You don't want to say things that are too redundant. So we impose some constraints on the solution, on the space of solutions. And so we formulated these as a more complicated optimization problem. But the basic idea is this one. And if you're interested in reading all the other linguistic constraints that we used, like trying to generate variable length sentences, because now if we just do dynamic programming, then maybe we have to pick one piece of text for each position. Maybe we want to generate also variable length descriptions. And here is a reference for the general framework of our sentence generation system. And here are references for all of the other work that tries to go deeper in some of the details about how to apply linguistic constraints of various types. And this is joint work with with the NLP lab of Professor Jae-Jin Choi, who's now here at the UW. Here are some results. Here you have this image, and it says, this is a sporty little red convertible made for a great day in Key West, Florida. Yes?
So, you had a score of 0.4 for the looking for food.
Uh-huh.
How did you get that score? 0.4 looking for food?
Right. So we got this score by finding the similarity between this object here and another object in the database that had this piece of text associated with. And we used feature descriptors like hog and sift. So if the object is in more or less the same configuration, you will get these piece of text in the description.
And the same applies to on the lake 0.6 and near Chapel Hill 0.5.
On the lake would look at the things, would not compare the features of the object, but would look at the things that are surrounding the object. Right? And the noun phrases use very similar feature descriptors as the verb phrases. So these two are using more or less the same similarity metric, but the pool of object detections that we use is completely different. So the method is data-driven. So here you are returning these phrases from objects that look like this one, but these are objects that have noun phrases applied to them. And here we have a more restricted set of detections that we use for retrieving these pieces of text, which are only objects that have some verb phrase applied to them. These are objects that are more likely to be depictions of birds doing something, as opposed to just standing there.
So for an input image, all you run is the noun detectors, or are you running any other detectors or classifiers? Given a new input image?
Given a new input image, we just run first the object detectors, yes. Which you could think of noun detectors. Yeah, we don't run action classifiers necessarily. Yeah.
So
the action is determined data in a data-driven fashion. Right. Yes?
So you seem to have quite a few specific locations, Chapel Hill, Long Island.
Oh, these are just made up. I mean.
But I imagine it's very hard to have an accurate.
Yes, it is very hard, but I mean, you still get some high-level ideas here. Like, you wouldn't find a beach near Chapel Hill, because Chapel Hill is very far from the beach. So the text will tell you, nobody's talking about beaches with North Carolina together. So these probably have a low compatibility score, but beach with Long Island probably have a high compatibility score, right? But yes, I mean, some of these very specific information will not be correct for that image. Because with this image, I mean, you can probably not tell what beach is that, right? And so one of the further work that we did is generalizing image captions, where we try to clean our data set from these very specific references in case you don't want them, right? So we can switch them off. But switching them off turns out to be a problem on itself. I mean, we wrote a paper for that. Because if you just remove the location, then the sentence will get broken. So you have to be very careful about what parts of the sentences you remove without breaking down the whole sentence. Anyways, here is the other example for a method. This one says, "Is a brass Viking boat moored on a beach in Tobago by the ocean?" Yes?
So I think earlier you mentioned that the VPs, for the VPs you look at the object itself, and for the PPs you look at the context.
Yes.
But there may be verbs that are indicative of the context, like a dog chasing a cat, or a bird looking at something.
Uh-huh.
So there may be verbs that are also indicative of context. How do you handle that? So in order to generate a verb phrase like a dog chasing a cat, you have to not only look at the dog as an object, but at the cat, which is, in this case, context for the dog, right?
Right. So the verb phrase would handle the chasing part,
Okay.
right? And the prepositional phrases would handle what is it chasing. Or actually, we're not, you're right, actually we're not very good at handling object-object relationships. Right.
Because there is no preposition.
Uh-huh.
Phrase there,
Right, right. Yeah, we try to do something on that regard in this paper right here, even in ACL 2012, where we had, but it doesn't work as great as you suggest. I mean, we had here one sentence for each object, right? Which is not probably the most natural way in which people would describe it. But we try to select what are the things that will be mentioned. So if there is a dog chasing a cat, maybe that will be mentioned. But if there is also the cat being chased by the dog, maybe that's too redundant and we won't mention that. But I mean, certainly there is a lot of more work, and people have worked on this problem later. Again, these are descriptions. The descriptions we generate are completely new. Well, actually not completely new. These are pieces of text that were stitched together, right? So it could generalize to more, visual depictions of the world. But we can also make more mistakes, like this one's here. One of the most shared in the wall of the house, where you find things that are in the picture, but the sentence doesn't make sense. Or you can have, here you can see a cross by the frog in the sky, which it just doesn't seem plausible. Yes?
Just a quick question, if you can go back to the previous slide, because you were showing an example of this issue about locations. So it's pretty impressive that even in a particularly good case, it decided that that was a beach in Tobago. It looks to me like it could have been in any of a number of places.
Right.
Is that just lucky, or is Tobago visually distinct from, I don't know, Hawaii, etc.?
I don't think we have enough data to really build good models for each of these locations. And there are certainly people who are trying to come up with rough locations given an input image using huge databases of places. And we could certainly try to use something like that. And here is just what happens to be returned. I mean, this could be a beach, and maybe in the database we had a picture of a beach that looks like this, and that beach was in Tobago, and that's why we return it. Yes?
So do you have a sense of how many new sentences you actually generated compared to the sentence that already exists in your data set? Or other way of asking this is that how strong is your language model compared to universe, and how do you trade them off? Because I would assume that if you put more emphasis on your language model, you would end up generating sentences that are more similar to the ones that exist in your corpus.
I don't remember right now if we had a particular experiment about that, but I would be surprised if we get 4 pieces of text that all come from the same image, right? And people have got interested in this problem very recently. And a lot of the work I show you is work we did in 11 and 12, 2011, 2012. 2014, it seems like a lot of people have started to work in this problem. And this has been fueled by 2 things. One of the things is that Microsoft released a huge data set of images with descriptions. It's called the Microsoft Cocoa dataset. And these images are curated. I mean, they are very high quality because they pay people to write them. And they did so for a lot of images. So this maybe was very expensive. And there is also a lot of progress recently on image representation and text representation, fueled by the ability to train very complicated deep layer architectures using neural networks. So those are 2 advances that have made people think maybe we can do now much better at generating descriptions for images. But it seems, I would point you to this paper here, which is also a very recent one. A lot of these things are in archive now. These are papers that probably will come up this year. This paper from this group in Switzerland called phrase-based image captioning has a very simple approach to the one very similar to the one I just presented, where they use n-gram models to stitch phrases together. So the way they get the phrases is not completely data-driven. They also use some of these convolutional neural network models to return the phrases, and then they stitch them together using a very simple model, like the one I presented. But despite the recent interest, I mean, there is still the problem that this is a task that is hard to evaluate, as I pointed before, and people have been trying to borrow text similarity metrics from machine translation, like BLEU or Whoosh or Meteor. And there is a lot of, I mean, these metrics, I mean, the people who work in these machine translation problems, I mean, don't like themselves. And in the language generation problem, I mean, they still are not perfect either. And the other way people have been trying to evaluate is ask people, I mean, how do you think this sentence fits for this image? But then that turns out to be very subjective. So to the next problem, referring to objects in, yes? Right.
Can you comment on the dataset part? Like if, say, instead of MSR Cocoa, they use your SBU caption dataset, this CNN, how would the performance vary? Like, I just want to understand the dataset.
How would the performance vary?
Like, I mean, your thoughts on, like, replace Cocoa with your SBU dataset, what would happen?
I think some of these works tried our dataset actually. Like the Toronto paper, and this is one that was one of the earliest ones that's published in ICML. So they use our dataset actually to train, but they were training word embeddings that were multimodal, or how do you generate vector representations for words so that you can use these vector representations to compare similarity between words. And they also had some language generation component. I cannot speak for them about how do they compare with using Microsoft Cocoa right now, but I would suggest you looking into that one because they are using our data set. And the Google people, the Google paper also had they had some experiment on our data set where they show some improvement. But the improvement was not as large because it's hard to evaluate on our data set because the sentences are written by people on the wild as opposed to sentences written by, and also we have only one sentence per image, and Microsoft Cocoa dataset has 5 sentences per image. So the numbers will be different. So it's hard to compare across.
Does that matter? Having 5 sentences, does that matter?
For evaluation, yes, because it will give you different numbers, right, that you cannot compare across. Referring expressions, okay. So we have this image here. We ask people to describe this object. And we get, this is what we get. The blue truck in the bottom right corner, the blue truck on the right, or the light blue truck. And the interesting thing is that with only 3 examples, you already start to see some patterns. Color seems to be important. They mention blue. Location seems to be somewhat important. And if we hide the arrow again, we can find back where the object was. And so this allows us to collect a huge data set of images with referring expressions, because now we can easily ask somebody else to verify the expressions. And referring expressions are these things that have been studied in the past for very long. And there are some data sets that people have come up with to study how people refer to objects. Some of the earlier work was concentrated more in these synthetic computer-generated images. And some of the later work has looked at more realistic scenarios. And the problem has been studied from different kinds of perspective, how people use color to refer to things, or relative locations, or how they use size modifiers, or how to refer to multiple objects at the same type. But a lot of these data sets are not capturing the things that we are interested in, which are real-world scenes. And a lot of these data sets are actually very small to learn some of the models that we wanted to. Because we want to have something that works for very diverse real-world scenes that have many different types of objects that we find in the real world, not in a laboratory setting. And we also want the images to be complex so that there are many objects of the same type in the image, so that you cannot just say, oh, the dog, and get away with it. I mean, you have to specify more things. And we want our data set also to be reasonably big so that we can learn some useful models. And this is these are images from the IAPRTC12 data set, and 20,000 images, but a lot of these images have many objects in each of them. And the nice thing is that the objects are labeled, so we don't have to label the objects ourselves, but we can just collect the referring expressions. And the way we collected the referring expressions was actually using a game. And the game works in a very similar fashion to the way I described before how referring expressions work. And this was an online game, and it's a game where player 1 would see a screen like this, where they would see an image and an object that is outlined, and they write a referring expression, orange bottle on the right. And then player 2, who's somewhere else, this is an online game, would see the same image, but without the outline, and he would see instead the referring expression that player 1 input, and then he has to localize the object. And if he finds the object that was outlined for player 1, then they both win points, and they switch roles, and they keep playing. So it's a cooperative game, very similar to other purpose-driven games like the ESP game or Image Labeler. And here is the description of our data set. We collected 130K referring expressions for more than 90,000 objects in almost the entire data set, 19,000 images. And this is work we presented in MNLP last year. And there are many things I could say about referring expressions. I mean, they are useful in robotics. People in robotics have used referring expressions a lot. They have studied them because this is very similar to the way you issue commands to a robot. You have a table, you have a bunch of objects. You can say, pick the red pencil or the blue pen. And in human-computer interaction, they are also potentially useful because you want to give people feedback in the way using language sometimes. you don't want to just give people the code for a book. Let's say you're going to a library. You want to tell them, this is a book that is in the second floor at the end of the hall in the top shelf, the blue big one. Things like that, as opposed to just give a code. I mean, so referring expressions are useful in many ways. And referring expressions that look human, that don't mention every possible attribute, are also interesting. So we presented a baseline here that is mostly about NLP. I mean, you assume that you have an image that has all the objects outlined and labeled, and you have a target object that you want to talk about. And this is the input, and the output is a tuple with 7 entries. And these entries refer to various attributes that you can choose to mention to tell this object apart from the other objects, including the name of the object. And here's one output, one example. The white truck in front. So you mention truck for the name of the object and white for the color of the object, front for the absolute location of the object. And you have also relative location, relative object if you want to say things like on, that would be relative location. On the street, that would be, street would be the relative object, right? And the way we formulated these is by defining a compatibility function that measures how the affinity between the input, target object, and scene with a tuple R. And we find the R that maximizes this compatibility function. And we subject also these output to some constraints. So if we have a scene that is very complex in nature, that has perhaps many cars in there, then we want to allow for referring expressions that are more verbose, that mention more attributes. While if we have only a single car, maybe we want to constrain that to a more limited set of attributes that get produced. And these are things that we learn from the data. And the compatibility function f has 3 components. The first component is a content-based potential, where we compute a distribution of various words that can be mentioned for each of these attributes: color, size, absolute location, relative object. Again, we have access to the size of the object because that's given as an input, and we also have access to all the other information like the location or the color histogram. Yes? People prefer other types of attributes as well. So we try to model these distributions of how people mention different attributes for different types of objects using this potential. And the third potential is a prior potential that is based on pairwise interactions between attributes. In these models, if we already mentioned the color in the referring expression, how likely are we to mention the size, for instance? So this is what gets captured here. And we also compare these to a baseline that comes up with referring expressions purely based on the text statistics without looking at the image at all. So we just stripe down the content-based potential. And I'm going to show you what's the effect of that in the following slide. Here are some examples. Here you have an image, and you have a door that is outlined. And the baseline method says the white door on the right, it doesn't have access to the location or the color. So it just guesses based on the doors that are in our data set that since more doors are white and most doors are on the right side, then this is the most likely referring expression. And the most common attributes that people mention for doors were the color and the absolute location also. So it chooses to output these two. The full model outputs something very similar, but it corrects the location because it has access to the location here. So based on the location and the relative size of the object with respect to the image, most people mention middle for objects that are around this area. And another interesting example, and this is the things that people came up with. So there is at least one person who said white door in the middle. And these are another example where the baseline method says the white picture on the right, and the full method has access to the color histogram of these objects. So instead of trying to correct it because it doesn't look white, it outputs a completely different set of attributes on the wall, which is a relative location and relative object. And these are what people say, so at least somebody say picture on the wall. So these are cases where we produce things that were very similar to the things that people said. Yes?
The fact that you didn't stop at just saying picture because that's the only picture in this image is because of the BI is misestimated? Or?
Yes, yes. We overestimate the length of the sentences. We produce sentences that are perhaps more verbose than what most people would say. Yes. And here is another example where the full model says the brown building in the middle, which maybe we can agree that's correct. But when we ask people about that image and that particular object, people mention completely different things. So here, our method totally failed. We didn't even get the name of the object right. And here we have another example where the method says a man on the left in the floor. And probably it should be on the floor. But even if you correct that, nobody mentioned that. That's kind of obvious information. People don't mention this kind of very obvious information that some person is on the floor. So we got that right. But what I want you to focus on is that we got the name of this object wrong. Building. People call it house. So there is some idea between the connection of the visual nature of objects and how do we map them to categories. And this is the last part of my talk where I talk about learning how to name objects. And this is related to work on psychology on entry-level categories. You have an object and there are many names that could apply. You usually prefer one. We usually prefer one of them. So researchers like Ross and Kosling did a lot of experiments in the context of psychology on entry-level categories. And entry-level categories are the categories that people are likely to name when presented with a depiction of an object. The things that you most readily recognize. And Ross ran experiments where she would show a picture of, let's say, an apple, and she would ask people to categorize that among 3 categories, for instance, apple, chair, or something like apple or chair. So they have to decide between these 2. The people did it very quickly, but when she asked to categorize the object between fruit and furniture, then it would take them a little longer to make that classification. So there are some categories that we can categorize more quickly because are the ones that we first readily associate with objects. And these are entry-level categories. Kosling further refined the notion of these categories that we readily map because for very typical objects like this one here, you can call it a bird. But if you have an object of the same category that is also a bird but is a less prototypical object, then you might go one level down in the semantic hierarchy of concepts, if you will, and you would call it with some name that is more specific, penguin. So how is this a hard problem? So one way we looked at this problem is how do we go from concepts that are very detailed to concepts that are the ones that people actually use. And as we saw before, if you have something like a cormorant, you probably would call it a bird if you see it. But for some other objects within the same branch, you might not want to go all the way to bird. You want to stop here at penguin. So it's unclear where is the right level of granularity that you want to use. What is the right level of detail that you want to use when you name things. And also, some of these concepts don't necessarily fall under the set of hypernyms for the object. If you see a daisy, you would call it a flower. If you see a daffodil, you would also call it a flower, but they're not necessarily under flower in this hierarchy. And this is a part of the wordnet hierarchy, which is a very popular tool that people use in NLP. It gives you it maps all the words in the English language to this semantic structure. Here is one example of what we want to do. We have an input image, and we have a large-scale categorization system, maybe using neural networks, that produces these words: corn crib, oast, farmhouse, log cabin, or dacha. And these are all more or less correct words if you have a very extensive vocabulary. And these are the actual things people say when they look at this image. And these are aggregated across several users: barn, building, fence, house, tree, yard, which seem more natural for us to relate to. And so the other problem we looked at is how to go from these type of outputs to these type of outputs without having to retrain perhaps the whole system that does the large-scale categorization. And the large-scale categorization system, this is what it looked like when we started working on these in 2013. You have an input image, then you compute a set of local descriptors using gradients, orientations, and histograms, and then you do some spatial pooling and coding, and then you pass that through a set of linear classifiers, any kind of classifiers. And then you come up here with a very large set of noisy predictions for categories. And we use around 7,000 categories that were at the finer level on the ImageNet hierarchy, which is a subset of the WordNet hierarchy. So these are very detailed concepts, 7,000 very detailed concepts. And more recently, we have replaced this whole pipeline with more powerful representations using convolutional networks. But at the end, you get the same thing. You get 7,000, more than 7,000 predictions for various very detailed categories. And the first approach we tried was to take these outputs and put them back in the WordNet hierarchy, and then propagate the scores up the tree. So if you output words that are closer to the root, then you're less likely to make mistakes, but you also will give me information that might not be too useful, because to me it might be more useful to know that this is a dolphin than to know that this is an animal. Imagine that you're only dealing with pictures of animals, then saying animal all the time will get you the right answer all the time, but will not be very informative. So there is this paper in 2012 that came up by one of our collaborators who worked on how to trade off accuracy and specificity, or how to output the words in this tree structure that maximize some accuracy, so you don't make a lot of mistakes. And we complemented this model by also taking into account what we call naturalness, or how common are these words in text actually, and use that as a proxy for word naturalness. So the idea is that if a word or sequence of words get mentioned a lot in text, then maybe that's an entry-level category. So we build this attraction or preference to certain nodes in the tree into this trade-off function, and we use that to generate our naming. So we also try to predict things that are in between, but we have certain preference for certain nodes in this tree structure. And the other approach we try is to take these outputs from the large-scale categorization system and instead learn models directly from our data. So we have, again, our million image data set. So we use it again for this project. And we find the most common nouns in this data set, which are probably also, again, good candidates for entry-level categories. And we learn models by, again, by taking these as our inputs. And then we learn models for tree, let's say, by taking all the as positives, all the images that mention tree in the caption, and as negatives, all the images that might have trees, but they don't mention tree in the caption. So now it's very similar to the previous model, but now we don't use all the tree words here to predict the word tree, but we also use other categories. For instance, categories like birds were very helpful to classify trees, and some types of even mammals, probably like monkeys. And if you have things like instruments, maybe that tells you that somebody will not mention the tree if there are some other occluders in the image. So this idea is not captured by propagating visual estimates along WordNet. And here are some results. I mean, you have this image, and then these are the labels that people input for this image. And these are the outputs of a large-scale categorization system: gelding, yearling, shire, yearling, draft. So if you are a fan of horses, maybe you will recognize these words as correct, or more or less correct. But these are the things that people actually said. And they are a completely different set than what the system output. And these are the things that we produced using our various methods. And these are the things that the system we compared against produces, which are all correct. Equine, ungulate, these are correct words, but they are not necessarily the words that people would mention. So we choose to make some mistakes like cow, but in favor of retrieving some words that might actually get mentioned by people. And we are very successful at that. Here's another example. So let me go directly to results. I mean, you can clearly compute a precision and recall at k equals 5. These are the top 5 words that our methods produce. And I'm labeling in green the ones that are also mentioned by people. So at k equals 5, we can compute prediction and recall. So here is a figure where we compute precision and recall for k equals from 1 to 50. And the large-scale categorization system is very bad at producing, of course, the things that people mention. But even if you try to produce things that are more general but still correct, you're very bad at producing the things that people actually say. If we use this method that using WordNet and word counts, we get much better already without doing much retraining. And if we have extra data in the form of images with captions, which are things that we collected from the web, and we didn't do any detailed annotation, and we have some power to retrain models on top, then we do much better. But for k equals 1, surprisingly, there's not a lot of difference. Anyways, this is a summary of my work. I've worked on natural image descriptions. And I've talked to you about most of the stuff we did on referring expressions. There's all the other ongoing work. I'm trying to do referring expressions for images in the COCO dataset, which is something that is recently available. So there might be some referring expressions that might be more interesting for this dataset. And or work on learning how to name objects. I didn't talk much about how to do the purely language task where you go from one category to another category, but I show you some of the stuff we did in translating the outputs of large-scale categorization system to words that people actually use. Well, thank you, and I hope you enjoy the talk.
So I think for the sake of time, I ask people, if you have questions, please do it offline.